Hi everyone, in this video I'm going to talk about common source MOSFET amplifier. First of all, what is MOSFET? Remember, it is metal oxide semiconductor field effect transistor. There are basically two types of MOSFETs. One is NMOS. The symbol of NMOS is symbol of NMOS transistor is like this. Here, this is basically drain side, this is gate side, and this is source side. Current flows through drain to source here, and one characteristic feature of MOSFETs, gate current is 0. So if gate current is 0, what we see here in MOSFETs, an infinite resistance. Okay. Basically, a MOSFET has three regions in its operating point. One is cutoff region. One is cutoff region. It is the first one. In cutoff region, VGS is less than V threshold voltage, and when VGS is less than V threshold voltage, there will be no current passing through transistor, and transistor is in cutoff region. Second region is saturation region, and if you use MOSFETs for the purpose of amplifying, you use it in saturation region. In saturation region, we find ID current with this formula 1 over 2 UN Cox omega over L VGS minus V threshold square. VGS, the voltage drop here. So this equation is important. Generally, UN Cox, UN means electron mobility, and Cox is oxide capacitance. Omega over L, generally you can choose it. That means it is up to you, but UN Cox is a process parameter, so it is unique to process. Okay. So the third region for MOSFETs in its operating point is non-saturation region. In non-saturation region, the current relation is 1 over 2 UN Cox omega over L 2 times VGS minus VT times VDS and VDS square. So how can we tell whether our transistor is in saturation region or in non-saturation region? Basically, if we look at the VDS value, this is VDS. If VGS minus V threshold, and we call it V overdrived, is greater than VDS, then my transistor is in non-saturation region. But if VGS minus V threshold less than or equal to VDS, then my transistor is in saturation region. For amplifying purpose, we will use MOSFETs in saturation region. I mean, drain VDS will be always greater than VGS minus V threshold. That leads to higher potential at drain and then gate and then source. This was NMOS, and in NMOS majority carriers are electrons. So be careful. In formula there is UN. UN means electron mobility. Okay. Let's now investigate second type of MOSFET. It is called PMOS and its symbol is like this. In PMOS, source at the higher potential and then gate and then drain, there is still an ID current. Gate current is 0. This time we look at V source G, not VGS, V source G, because source at the higher potential. So in cutoff, so the first region is cutoff region, V source G minus. Also in PMOS, V threshold is negative. So we take its absolute value in the formula to make it positive. So in cutoff region, V source G minus absolute value of V threshold. Okay, let's write like this way. V source G is less than absolute value of V threshold. Second region is saturation region. In saturation region, V source G minus absolute value of V threshold is positive. I mean V source G is greater than V threshold. Also V source G minus absolute value of V threshold is less than V source drain. Remember, in NMOS case it was VDS. We compare it with V overdrive with this V overdrive voltage with VDS in NMOS type. In PMOS type we compare it with V source drain. Why? Because source at the higher potential. So saturation region formula remains the same in PMOS, but there is a little bit change. What's change? This time UP-COX. There is hole mobility because majority carriers are this time holes. This is hole mobility, UN-COX. You can choose omega over L and then V source G minus V threshold, absolute value of V threshold square. This is non-saturation region. Let's write our third region. It is non-saturation region. This was, saturation region. In non-saturation region, sometimes we call it linear region. Okay. V source G minus absolute value of V threshold is greater than V source drain. And also V source G minus absolute value of V threshold should be greater than 0. This is the condition where transistor not to be in non-saturation region. Okay, non-saturation region drain current formula is 1 over 2 UP-COX omega over L 2 times V source G minus absolute value of V threshold times V source drain minus V source drain squared. So what is small signal equivalent of MOSFETs? In small signal equivalent of MOSFETs, small signal equivalent. It's similar to BJT, but there is a little bit change. Here there is gate parts. Here this is VGS voltage. This is GM VGS. Generally here there is RD and R loads. This is V output, and here this is source. And there might be sometimes this transistor. I mean, this part is outside of the transistor. Transistor is basically this. This is our small signal equivalent of MOSFET. So why there is open circuit here? Because gate current is 0. Gate current is 0. There is open circuit here. So if you look from here, you see infinite resistance. Remember, when you look from here, there was RP resistance beta force over GM in BJT type. This is MOSFET, so do not, I am deleting this for not confusing your mind. So VGS, here our input, if you look at from here, you see infinite. This is VGS, there is voltage drop of VGS here, and the current, ID current, is GM VGS. This is small signal equivalent of MOSFET. And of course, this is for NMOS type. For PMOS type, remember, for PMOS type, PMOS small signal equivalent here again, this is my gate. Here, this is my source, but I'm looking for this voltage V source gate. There is current passing through from source to drain, and there is drain. What is this GM? This current GM V source G. Here comes to drain. Again, here there is ID current 0, gate current is 0, and you see infinite resistance. So this is small signal equivalent of PMOS. I mean, okay. So what is important here to note, what is GM? GM is 2 times Kn times ID. So in MOSFETs, into MOSFETs type, GM parameter is equal to 2 times Kn times ID. What is Kn? Kn is UN Cox omega over L. Remember, in BJT case, GM was equal to IC over VT. In this case, GM is equal to square root of 2 times Kn times ID. In both cases, PMOS and NMOS, this formula is valid. Okay. So let's now investigate our common source amplifier in DC case and AC case. Remember, when we do DC analysis, capacitors are open circuited, so there will be no current passing through this side. So also remember, gate current of MOSFET is 0. So there will be no current passing through this side, and there will be no current passing through this side. The current will pass through this side. There is a voltage drop, and I can find V-gate in DC analysis. It is VDD times R2 over R1 plus R2. And if I know V-gate, I know V source here is grounded, so VGS equals V-gate. And always VT is given in the question. So how can I find the DC current ID which flows from drain to source? It is equals to 1 over 2 UN Cox omega over L VGS, which is equal to VGS minus VT square. VT square. That was the DC analysis, and it is easy like this. So remember, we will now do the AC analysis of common source amplifier. In AC analysis, remember, capacitors are short-circuited. And also DC voltage sources are grounded. So this is short-circuited and VDD is here grounded. So in DC case, my circuit becomes here my V input signal, there is RS, it comes, R1 goes ground this way, R2 is ground this way, so R1 will parallel R2. So my AC signal equivalent of transistor is like this. There is V input, here R source, R1 parallel R2, this is V gate, and here my source, and source is grounded. There is, GM VGS here, and RD goes ground in here. So remember, when we do this analysis, we found ID. What was GM? GM was equals to square root of 2 times ID times Kn. I mean Kn is equals to UN Cox omega over L, and this is known. So we calculated ID, so we can calculate GM and pass to AC analysis of this circuit. So remember, this is VGS. So what is input resistance in this case? Input resistance is V input over I input. So here there is actually I gate which is equals to 0, so I ignore it. So V input over I input equals where do I look it from? Here it is R source parallel R1, no, sorry. Actually, I do not include R source in. Generally, we do not include R source in input resistance. Let me think if we include it or not. Input resistance depends on your, definition. If you look from here, we don't take the RS. Here, we take the R input, look from here. So my R input becomes R1 parallel R2. So what is my output resistance? For output resistance, we make V input, voltage source short-circuited, and then there is RS, and then there is R1 parallel R2. These are short-circuited, so there will be no current passing through this side. So this is also, V gate is also grounded, source is also grounded, here source. So GM VGS basically becomes 0. Why? Because VGS is 0. Gate is here 0. Gate is here 0. Source is 0. GM VGS is here 0. So my circuit for AC case becomes like this. There is GM VGS. This current is 0. Sorry, this is R source. Gate is 0. The resistance I look from here. I mean not here. So if I connect V-test and divide I-test, what I see that here, sorry for my bad driving. Remember, we shut down the independent sources and connect a V-test voltage here, and if we divide V-test over I-test, there will be no current passing through this side. Our output will become equal to RD. So one last thing remained, which is gain. So how can I find the gain? So I will copy this. So to calculate gain, what we should know, gain is equals to V output over V input. So this has two parts, V output over V gate and V gate over V input. So I know V gate over V input. When I look to the circuit, V gate over V input equals, there is voltage divider here, R1 parallel R2 over R1 parallel R2 plus RS. So what is V output over V gate? So V output equals minus GM VGS times RD, here minus, because current comes through here from ground. So VGS equals V gate, because source is grounded, and this is equals to, I mean, I do not write to something. VGS equals to V gate. So V output over V gate equals minus GM VGS times RD over VGS, because V gate equals to VGS and VGS cancels. So gain in common source amplifier equals V output over V gate times V gate over V input, and that is equals to V output over V input, and that equals to R1 parallel R2 over RS plus R1 parallel R2 times minus GM RD. So gain is negative. That means there is a 180-degree phase shift between input and output. That is it, guys. Thank you for listening. See you at the next video. Take care of yourself.